Probability is not something you think that you would use very often in quality management. You think more along the lines of, are my data looking the way I want to, not what's the probability that the next data point is going to come up a certain value. Well, probability is used actually quite a bit when we do sampling, and it's important that we understand probability so that we can sample properly and make sure that our sample is representative of our actual total population. So let's talk a little bit about probability, what it means, and how it's used in sampling. So in this lecture, we'll define probability, and we'll look at calculating basic probabilities given a situation. Probability is the chance that a given event will occur. So for example, if you think of flipping a coin, you've heard the probability of getting heads is 50%. A trial is the performance of experiment. So that would be the actual flipping of the coin. The outcome is the result of a particular trial. So that would be, for a coin flip, getting heads or tails. And then the event is a collection of outcomes. Now these events can have one or more outcomes. Let's look at 5 socks in a bag. We've got 2 red socks, we've got 1 blue sock, and we've got 2 green socks. So the event of pulling out a green sock has 2 outcomes because we have 2 socks in that bag that are green. The total number of outcomes is 5. So if we look at the probability of pulling out a green sock, that's 2 socks out of 5 socks total, or 40%. And that's what we mean by events. Sometimes things get a little bit complicated when you have lots of stuff to pull out of. So keep in mind what your event actually is when you're calculating probability. Mathematically, the probability of some event A happening is the number of successful outcomes of event A, which means A actually happens in your trial, divided by n, which is the total number of successful outcomes. So that's all the things that could happen. So to calculate your probability, you need to know n sub A and n. Keep in mind this is a finite n, so n is countable, whether it's 50 or 1,000 or 10,000. This is not practical for an infinite n. And an infinite n in terms of food processing would be something like cans coming down a line in a continuous process. You can't really say, I have 10,000 cans here. They just keep coming. So for practical purposes, that is an infinite n. And if you're trying to figure out probabilities in those cases, you need to use probability distributions like the binomial distribution. This is beyond the scope of this course. We will not talk about probability distributions, but keep in mind when you have an infinite n, this definition doesn't apply. Let's take a look at an example of probability with a finite n, just so you can get used to reading problems and seeing where these numbers come from in the problems. So we've got a container of parts, 50 in that container. We know there's 10 non-conforming units in there, so they're either the wrong size or they've got some kind of scratch or dent. They're just not going to work. So we pick a part, we return it to the container, and we record the number of trials and the number of non-conforming. Now keep in mind that we still only have 50 parts total, and we know that only 10 of those are non-conforming. We're going to use this when we calculate probabilities. So we do this 90 times. And we find 16 non-conforming units. So we want to figure out the probability of selecting a non-conforming part based on the known outcomes and the experimental trials. Okay, so these word problems are usually fairly long like this, and we have to go through and pick out which numbers are important. So let's focus on the known outcomes first. Here they are. So we know that there's only 50 parts in our container. So that is our total n that we know about. We know that 10 of those are non-conforming. So regardless of how many trials we do, we know that there's only 10 parts that are non-conforming. There's not going to be one extra part magically appearing as non-conforming. So if we base this on our known probabilities, this is our population, basically. So we know that there are 10 non-conforming parts here out of 50 parts total, so that gives us about a 20% chance of picking a non-conforming part. Let's look at the number of experiments. So when we talk about our experimental data, we did this trial 90 times. So our total amount is 90. We picked 16 non-conforming parts out of that 90. So our experimental n sub a and our experimental n are different than our known, or our population. And this is known as our sample data. So the probability here of picking a defective part is 16 divided by 90, or 17.8%. Notice this is different than our total population data. It's close. It's around 20%, but it's not exactly the same thing. And the interesting thing about this is the more trials you do experimentally, the closer you're going to get to your population data. Keep that in mind when you're thinking about sampling and creating sampling plans. The more experiments you do, the closer you're going to get to your actual population. But that means there's more expense and more time involved in testing. And so one of the things to think about with sampling is, when is enough enough? When have I tested enough to be fairly certain what I've got in my box, but I haven't tested so much of the material in my box that I don't have anything left to sell?